I think the special theory of relativity is fun. The Einstein, he's famous. There's nobody in here, I'm sure, that hasn't heard of him. And he's most famous for his special theory of relativity stuff. You know he actually won the Nobel Prize in physics? Probably knew that. It wasn't for this. It wasn't for general relativity. It didn't have anything to do with this cool space stuff. E equals mc squared? Nope. Anybody happen to know what he got the Nobel Prize for? That's right. The photoelectric effect. Where if you have light with enough energy, a high enough frequency, not just any old light, not just bright light, or really intense light, it has to have enough energy, then it can eject electrons from metals. That was revolutionary. It's probably that and Brownian motion are his most quoted papers, actually. He wrote them all around the same time, but yeah, I find it interesting. That's what he got the Nobel Prize for, not this relativity stuff. Yet, this is what he's more famous for. And without it today, we wouldn't be able to use many things. We rely on it. We have to account for it. Your phone wouldn't be accurate if we did not account for the special theory of relativity, as well as the general theory of relativity. Satellites in general wouldn't be able to. So, yes, I'm not going to make you experts at the special theory of relativity between today's lecture and next Monday, but you'll know what it is now and some of the cool consequences or the befuddling consequences of it. So, to start with, to give us some good background and definitions and to get you in the feel for what we need, I'll get to these. I'm going to start with quite a few little videos. And it's fun because this one was made like before I was born, but it's really good. It works. So we're going to watch several segments here, and then we'll be able to discuss.
You're used to seeing things from a particular point of view, that is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look you. Under different circumstances. You look peculiar. You're upside down. No, you're the one that's upside down. No, you're upside down. No, I'm not. He's the one that's upside down, isn't he? Well, let's talk for it. All right. Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now. All right. My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands. This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me. All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the Earth as fixed, and walls are usually fixed to the Earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the Earth is the most common frame of reference in which to observe the motion of other things. This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is the position of any object such as this ball can be specified using these 3 reference lines. This reference line points in the direction which we call up, which is a different direction here than it is on the other side of the earth. And these 2 reference lines specify a plane, which we call horizontal or level. In this film, we're going to look at the motion of objects in this Earth frame of reference and in other frames of reference moving in different ways relative to the Earth frame. Well, let's look at a motion. This steel ball can be held up by the electromagnet. Now I'm going to open the switch and you watch the motion of the ball. The ball is accelerated straight down by gravity along a line parallel to this vertical reference line. As you can see, the electromagnet is mounted on a cart that can move. I'm going to do exactly the same experiment that Dr. Hume did, but this time while the cart is moving at a constant velocity. The cart is pulled along by a string which is wound around this phonograph turntable, and that pulls it with a constant velocity. When the cart passes this line, the ball is released, as you can see. I'm going to start the cart down at the end of the table so that by the time it gets to this point, I can be sure it's moving with a constant velocity. Now, I want you to watch right here so that you will see the ball falling. I think you can see that the ball landed in exactly the same position that it did before, when Dr. Hume did the experiment with the cart fixed. But this time, the ball could not have fallen straight down. Let me show you why. The ball was released. At that point, if it had fallen straight down, because the cart moves on and the time it takes to fall, it would have landed back here somewhere. But it didn't. Now I'm going to do the experiment again. This time, I'm going to let you watch the motion through a slow motion camera.
So, why did it not fall straight down? Very good. We did that similar demo last time. It already has horizontal velocity when it was released. So they just added to that, and it moved horizontally and vertically at the same time. We'll get to see that again. Better with this.
Here, the cart moves by, the ball will fall, and you can watch in the slow motion camera. I'll show you this again. This time there'll be a line on the film so that you can see the path. I think that you can see that the path of the ball is a parabola. But all of this has been in a frame of reference fixed to the Earth. How would this motion look in a frame of reference which was moving along with the cart? Frame of reference like that. Well, so that you can see what it looks like, I'm going to fix this slow motion camera so that it moves with the cart. Like this. I'm going to do the experiment again. Incidentally, I'll start it, and then I'm going to stand here so that when the ball falls, you will have something which is fixed as a reference point. In the moving frame of reference, I think you can see that the path of the ball is a vertical straight line. It looks exactly the same as it did
assumed that the experiment with the cart fixed. If we were moving along in this frame of reference and we couldn't see the surroundings, then we wouldn't be able to tell by this experiment that we were moving at a constant velocity. As a matter of fact, we wouldn't be able to tell by any experiment that we were moving at a constant velocity. So I'm going to do the experiment once more, and this time I'm not going to stand here behind the ball of the ball so that you won't have any fixed reference frame. As far as you're concerned, that time, the cart wasn't necessarily moving at all. That time, when you couldn't see the background, then I think perhaps it was harder for you to realize that you were in a moving frame of reference. The important thing to realize here is that all frames of reference moving at constant velocity with respect to one another are equivalent.
Let's pause there. So, they use the term frame of reference a lot. Do you have a good feel for what it is now? We're in a fixed frame of reference. If I'm moving relative to you, I'm in a different frame of reference. If I run around at a constant speed, I'm in my own frame of reference, but it's different than yours. Ones that they just showed, and I just mimicked, are called inertial reference frames. You know what inertia is. We're used to that. Everything I taught you is true. The special theory of relativity is based on two postulates, assumptions. Given these two assumptions, there's lots of funky consequences. And one is that in inertial reference frames, all of the physics holds. So in your fixed reference frame, you learn your physics. But if I'm running around at a constant speed, all the physics is the same for me. It's the same in every reference frame that's inertial. You would get what we'd expect. We'll show a little clip that'll show you what I mean with when it's non-inertial. But it basically means if something's accelerating, changing its speed, then we don't say it's inertial. It's non-inertial. And so the first postulate, he just said, there's no experiment then that can reveal absolute motion. He gives you the idea behind that. Another idea that Einstein did, he was famous for his thought experiments. You're used to gravity. Gravity pulls things down. So if you're in an elevator with no windows and you're just standing there on Earth, the elevator's not moving, you feel a force pulling you down to the floor. If you drop something, it falls. All the same physics we've been talking about. Now, what if you go out into deep space? The elevator is accelerating out in space. You'd be inside. Let's say it's on a rocket ship with some thrusters out there, but you're inside with no windows. This thing is accelerating. What would you, if it accelerates at 9.8 meters per second squared? Inside, what do you notice? No difference. It's accelerating up on you. It's like the floor is coming at you, right, at 9.8 meters per second. So it's just like the Earth pulling down on you with 9.8 meters per second. You couldn't do it. If you drop something, it would fall to the floor. In your frame of reference, you would see no difference. Similar to what he did there. If you have no reference point, there's no experiment. And trust me, that's what scientists, they're still trying since actually even before Einstein. But we've never found an experiment that can reveal absolute motion, meaning these frames of reference, there's no preferred one. There's no like, oh, well, here's the main frame of reference, and all the others are just moving relative to it. No one is special. It's all that motion's relative. It's the motion between reference frames, not that yours is the most important and I'm just auxiliary. That's the first postulate. All physics is the same in all inertial reference frames. There's no test you could do to determine whose frame is correct, or the main one, or more important than the other or not moving at all. Does that make sense? All right, let's continue on then with a little more. Any questions?
I showed you what the motion of the ball that was released from the moving cart looked like.
Where's my... Whee! There-ish.
Completely adequate. So far, we've been talking about frames of reference moving at a constant velocity relative to one another. Now I'm going to do the experiment with the dropping ball again. Only this time, the cart will be accelerated relative to the Earth frame. These weights will fall and give the cart a constant acceleration. Put the ball up, and then I will release it. The motion is very fast, and I want you to watch at the point where the ball is released from the fixed camera. Ready? I don't know whether you saw that or not, but the path of the ball was the same as it was before, only this time it landed in a different spot. This is because the car kept on accelerating in this direction as the ball was falling. Now I'm going to let you see it again with the slow motion camera fixed onto the car. This time you saw the ball moving off to one side and not following down the vertical reference line as it did in the constant velocity case. Now suppose you were in this accelerated frame of reference. How could you explain this motion? Gravity is the only force acting on this ball, so it should fall straight down. But if the law of inertia is to hold, there must be a force pushing sideways on the ball in this direction to cause it to deviate from the vertical path. But what kind of a force is it? It isn't a gravitational, or an electric, or a nuclear force. In fact, it isn't a force at all, as we know one. So we're left to conclude that since there is no force that could be pushing in this direction on the ball, that the law of inertia just does not hold. This is a strange frame of reference. We call a frame of reference in which the law of inertia holds an inertial frame. The law of inertia holds in the Earth frame of reference, so it is an inertial frame. The cart moving at constant velocity relative to the Earth is an inertial frame. But the cart which is accelerated is not an inertial frame. Because the frame of reference that we're used to living in is one in which the law of inertia holds. When we go into a non-inertial frame, like the frame of the accelerated car, our belief in the law of inertia is so strong that when we see an acceleration of the ball sideways, we think there is a force causing it. So we make up a fiction that there is a force. And sometimes we call this a fictitious force. Fictitious forces arise in accelerated frames of reference. The frame is accelerated in this direction, so you in the frame see an acceleration of the ball in this direction, and you say that there is a force causing it.
All right. So do you understand the difference between inertial and non-inertial reference frames? The special theory of relativity applies to inertial reference frames. The general theory of relativity, which your book covers and you're welcome to read it, is more about the non-inertial frames and gravity, accelerations. But for inertial reference frames, all motion's relative, all physics holds in each of those frames of reference, and there's no frame of reference that's preferred. Second postulate for the special theory of relativity is, how I sum it up, the speed of light is a constant. It's the same for everybody. You're like, yeah, so that makes sense. Let me make it a little weirder. Some of you have mentioned it before. If you're in a car and you toss the ball up, whoosh, it stays with you. It's just like that. Because if you're going a constant velocity, it already has that velocity. So I just give it an upward, so it goes in a nice parabola. If I accelerate, like that cart did, I can get ahead of it. Because once it's in the air, it doesn't accelerate, so it can't go as far as quickly. But let's say I'm on a train, and the train's moving that way, so I'm moving with the train. I'm standing still on the train, but the train's moving. If I throw this ball at 90 miles an hour, that way, and let's say the train's going 30 miles an hour. So the train's going 30, I'm going with it, and I throw the ball 90 miles an hour, how fast is the ball going relative to you? Is it 60 or 120? See, I'm in a different frame of reference. I'm moving at a constant velocity of 30 miles an hour on the train. You guys are fixed on the ground, the passerbys. So I'm already moving 30 relative to you. If I throw the ball at 90, I join your frame now. I can pitch at 90 miles an hour. Yeah. It's 90. But if I hop on the train that's going an additional 30, then it's 120 relative to you. Does that make sense? Now, if I'm moving that way, the train's going that way, and I throw 90 miles an hour that way, then the motion relative to you is 60. Right. Your gut and intuition's right there. That's how velocities add up. That's what we're used to. So now let me replace this with a flashlight. You got your beam of light. Here, I'll even do it for added emphasis. There's my light. If I'm on the train going 30 miles an hour, well, let's stop. Boom, I turn on the light. Choom, and it goes at the speed of light, which is like 3 times 10 to the 8th meters per second. It's really, really fast. All right, now I'm on the train going 30 miles an hour. I turn on the light. What's its velocity relative to you? Is it the speed of light or the speed of light plus 30 miles an hour? The speed of light. That's kind of weird. And vice versa if I've shown it the other direction. The speed of light doesn't add up like tennis balls or baseballs when you throw them. Or one truck moving relative to another truck. And we have not been able to observe it otherwise. They've done measurements. They're on fast-moving jets or a spaceship. And everybody, they go to measure the speed of light, they get the exact same answer, no matter which frame of reference they're in. So the idea is like you could never catch a beam of light, right? Have you heard that thought experiment? What if you were to ride alongside a beam of light? You turn on your flashlight, ding, and it's going at the speed of light. What if you're like next to it, moving with it at the speed of light? You're moving right along with it. What speed do you measure it to be? You would think it'd be 0 because you're moving with it. Anything else would. But for light, you would still measure it as going the speed of light. So in reality, you can't go along with it. Even in your faster reference frame, it would still be going at the speed of light relative to you. That's the second postulate. That's what they've observed. And so given these two things, let's look at some consequences. Here's a nice 2-minute little video on YouTube someone made, but it works. It's going to help explain what we... Oh, I'm sorry, yes. Yeah, you wonder, well, maybe the speed of light's frame of reference is the ultimate one, right? That idea. No, because... No. You can do some thought experiments like that, like you're in the frame of reference of the speed of light, going at the speed of light. We try to accelerate spaceships up to the speed of light. We haven't done it. Can't do it. But if you could, think about it. You would still measure the speed of light to be the speed of light. You'd think it's going faster than you are. Of course, in your frame of reference, you're moving with it. You don't feel like you're moving. It's everything else is moving relative to you. So it still doesn't make it any more special than others. Yes?
Can we measure the speed of light?
Honestly, one way, time it. It is really, really fast. So the easiest way to think about it, and I remember doing this in one of my physics labs, is we got in a long hallway, and we sent a laser down the hallway, bounced off a mirror, and came back just to double the length. You can even go back multiple times. So it's covering a big distance. Big distance. And we needed a really fast oscilloscope. So we knew as soon as we triggered it, and we knew when it came back. We compared the time between the peaks when the sensor picked it up, and it was very, very close. But there was a difference, and because now with better electronics, we actually measured it. Distance over time. How long it took to come back. That's one way. An oscilloscope. Oscilloscope. It's those things you see, the little boxes, whatever, and then there's a little screen where you see sine waves and cosine waves, or little bloop, 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 or up square waves. It measures how it's changing. But basically it detected when it left, and it made a little bloop, and when it came back, bloop, and they weren't in the same spot because time had elapsed. We measured the difference in time, and that worked. So this thing called simultaneity, where things happen at the same time, if you're in different frames of reference, maybe not.
Imagine two observers, one seated in the center of a speeding train car, and another standing on the platform as the train races by. As the center of the car passes the observer on the platform, he sees two bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time, so he concludes that the bolts were simultaneous.
And how does he do that? The distance is the same, the time's the same, speed must be the same, or it's because the speed's the same, the distance, you got that part. Shouldn't be anything funky there.
Since he knows that the light from both strikes travel the same distance to his eyes at the same speed, the speed of light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear. The train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear. But what does the passenger see? As her friend on the platform predicted, the passenger does notice the flash from the front before the flash from the rear, but her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct?
What do you think? Who's right? Let's see what
The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike. Einstein tells us that both are correct within their own frame of reference. This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity of events.
I'll relax that a little. Never? Almost never. let's just put it this way. Two events that are simultaneous in one frame of reference need not be simultaneous in a different frame of reference. And usually they're not. And here's a nice clear example. And do you see how it was based on the speed of light's a constant? If that's true, then they couldn't agree. Because she saw it first, given those distances and velocities, how long it would take to get to her. So yes, she literally sees the flashes at different times in her frame of reference. And the guy on the platform sees them at the same time. Neither are wrong. They're both right. They're just in different frames of reference. That's simultaneity. So I like thinking about it when I'm watching like Star Wars or Star Trek. And you got two ships and they're firing at each other. Who fires first? Well, that depends on their frame of reference. If they're both sitting there in the same frame of reference, not moving with respect to each other, then they're both going to agree who fired first. Yes? But what if one's moving near the speed of light and the other one's stopped, or a lot slower? You could have this situation. And you can get into trouble. Because you think the other person fired first, so you fire back, but then that person sees yours and thought you fired first, and you got into a battle because of this simultaneity problem. Different frames of reference. Theoretically, it could happen. So there is one nice thing about this. We don't have any frame of reference that's preferred, and events aren't necessarily simultaneous to people in different frames of reference. But comforting, what is the same for everybody? The speed of light. You've heard of spacetime? It's the ratio between space and time. What is the speed of light? Think of it this way. Let's do it over here. Distance over time. So you have space, the amount of distance you're going to cover, over time. That ratio is the same for everybody in different inertial reference frames. Because that's the postulate. That's how we got this example of simultaneity we just saw. So if you're in a different frame and something seems to happen at different times, then it covered a different amount of space, didn't it? You could have something cover a lot of space over here, but it's going to take more time to have the same ratio. That's the unifying factor between our reference frames. Einstein started thinking about it, and with relativity it helps to think of not just sitting here waiting for class to end, waiting for time to flow by like a river. As sleepy as some of you are. Start thinking of time as we move through it. Just like we move through space, we're moving through time, even if time isn't passing us by, we're moving through it. So we move through space, we move through time. This fabric of space-time. But the ratio between the two is going to remain the same. That's the theory of relativity. Questions? All right. Here's an animation. What we're going to do is, here's the spaceship's frame of reference at the top, and we're going to make a light clock. We're going to send a light beam up. It's going to bounce off the top mirror and come back down. It's a certain distance. We know the speed of light. We know how long it'll take. At the same time, from the Earth's frame of reference, we are sitting here in our classroom watching the ship go by. That ship's going to do the same thing. It's going to send a light beam up. It's going to bounce off the top mirror and come back down. This is a slow ship. Let's see what happens. Do it again. So the top one just goes up and right back down, just like we'd think. This says it took 4 nanoseconds for it to cover that distance at the speed of light. This one, though, it's kind of like the ball on the cart. If you're in the frame of reference of the cart, the ball looked like it curved. No, that was wrong. If you're in the frame of reference of the cart, it went straight down. You don't notice anything. It was when we watched it go by. That's what it was. Sorry. That's when it looked like it curved. Well, that's what we're doing here. We're in a fixed frame of reference relative to the spaceship, the cart going by, the spaceship going by. So what do we see? We don't see that light beam go up and down. Watch the bottom again. We see it go up and to your direction and to the right. Bounces off and comes down and to the right. So look, it traveled a different distance. Distance ct. What's distance? It's rate times time. So the velocity of speed of light c times that time. That tells you how far it went up. Similar down. That's the total time. It took longer, 4.1 nanoseconds. Yes, the special theory of relativity is not a big difference when you're going slow. Let's speed up the spaceship. Let's go half the speed of light. You can see now it travels even further. It covers more space when we watch it from our Earth frame of reference. So it's going to take even longer to go up and back down. It has to keep the speed of light the same ratio. This animation says it's 4.7 nanoseconds. And if you're going 90% the speed of light, you get the idea. You go even further. Watch this. From the frame of reference of the spaceship, it goes up and down in less time than it even took to go up from the other frame of reference on the Earth. So if you have, it goes up and back down. This one goes up and back down. This distance was the speed, velocity, times the time it took. That's how far it went. It did the same over here. If we say the up and down distance is the speed times the time in this frame, it's just the distance straight up and down. So we'll just call it T naught. To differentiate, it's a different time. How far did the spaceship go in that same amount of time? It went VT, the velocity of the spaceship. That's how much distance it'll cover in the time it saw the light going up, down. Are you with me? This gets a little more mathematical. If we watch the spaceship go for that long, it goes that far. And the same amount of time it took the light to go up and back down from our frame of reference in the Earth, watching it. This is nothing more than Pythagorean theorem. Who remembers that? When you have right triangles, B, A, C, A squared plus B squared equals C squared. For the interested student, no, I'm not going to hold you to this, but do that with these. This squared plus this squared has to equal this squared. It's a right triangle. When you do that, this is what it comes out to be. The difference in the times of the two reference frames, it differs by this factor. That's called the Lorentz factor. I wrote it over here. The Lorentz factor. And it's often given the Greek letter. I just brain lapsed what it was. Is that gamma? Gamma. So that's what it is. So you don't have to think of that scary fraction with the square root sign. But it's just a ratio of how fast the object's going relative to the speed of light. Look at it this way. If you're at rest, what's V? 0. So you put in 0 over speed of light, that's 0. 1 minus 0 is 0. Square root of, 1 minus 0 is 1. The square root of 1 is 1. 1 over 1 is 1. And you get the same times. So the special theory of relativity works at all speeds, less than the speed of light. It works at our normal everyday speeds. Why don't we use this at normal everyday speeds? Why didn't I introduce this when I did Newton's laws? Yeah, because Newton's law is much easier. Doesn't look as scary as that, does it? Newton's laws work, pay attention to this, Newton's laws work at slow speeds. They work, so use it. But realize Newton's laws do not work for motion when you're going near the speed of light. You'll be off because the time changes. Then you have to use the special theory of relativity. You can use the theory of relativity at slow speeds. It still works. It's just more complicated. But the special theory of relativity we have to use when we're going faster. You can see as you approach the speed of light, let's say you're going the speed of light. This is 1. 1 minus 1 is 0. Square root of 0 is 0. And 1 over 0 is 1 over 0. Infinity. So it gets, time slows down more and more and more and more in that other frame of reference. That's called time dilation. Time seems to dilate, get longer. So just like this example of the spaceship. If you're in the spaceship, you just see the light go up and down. It took 4 nanoseconds. But if you're watching the spaceship zoom by at near the speed of light, in your fixed frame of reference relative to it, you measure a different time. You watch the light beam go up, and you watch it come back down, you time it from your frame, and you get a different time. And the faster that ship is going relative to you, the bigger the difference, the bigger the Lorentz factor. And that's called time dilation. You've probably heard that with the theory of relativity. Time slows down for people when they go near the speed of light. Who's heard that? Probably before you got to my class. Okay, less of you than I thought. But the neat thing, though, is that people don't realize, if I had the mirrors here on Earth and I did it, what time would I get? 4 nanoseconds. T naught. That's the frame of reference over here. That's what I'd get. Okay, now I hop on the spaceship going 87% the speed of light, let's say. I don't know what it is. 87% the speed of light. How long do I measure the time to go up and down on the spaceship? I'm on the spaceship with it. 4 nanoseconds. Nothing's different for me. I'm moving, right? So nothing seems weird to you. But if the person back on Earth watching me thinks my time slowed down. What if I'm on the spaceship? What do I see for the person at Earth? Is the Earth moving? Relative to me. You're in the spaceship's frame of reference now. Are things moving in your frame relative to you? No. That's your fixed frame. You're at rest in that frame. The spaceship's doesn't look like it's moving. The stuff inside doesn't look like it's moving. Who looks like it's moving? The Earth. Let's look out the window. What do you see? It looks like the Earth is receding from you at 87% the speed of light, right? It looks like they're moving relative to you. Motion is relative. There's no preferred frame. So if I'm in the frame of reference of the spaceship and I see the Earth cruising away at 87% the speed of light, what do I measure? How long does it take their beam of light to go up and down? Right, the slow time. So as long as there's relative motion, are you seeing a paradox here, though? Who's right? Wait, someone at Earth looks at the spaceship's clock, light clock, and says, oh, it's running more slowly than mine. But somebody on the spaceship looks back at the Earth's light clock and says, oh, yours is running more slowly than mine. It seems like a paradox. How can both be right? Yeah, if this time is different, then does that affect our biological clocks also? Can it affect our age? Yes. We're going to discuss that more next time. I want you guys to think on this. It's called the twin paradox. Google it. You can be all smart by Monday. The twin paradox. Who's right? Well, at this point, both are right, just like the simultaneity. Time doesn't change in my reference frame. Time doesn't change in this reference frame, but relative to each other, your time looks different than mine, and your time looks different than mine. Because of those two postulates. Are you with me to this point? Oh, quicker than I thought. Where we're headed is, we'll look at this Lorentz factor and see how much the times change with that factor, how fast you're going. They do a nice chart in the chapter. There's another effect, and it's called length contraction. If time is changing, what else has to change? Space. And so we measure different distances in different frames of reference also in order to keep the ratio of space-time, speed of light, the same. So yeah, it can look like times slow down and lengths get shorter with this relative motion. Now, I'll admit, this special theory of relativity is fun, but most people haven't thought about it before, so I encourage you to read it and think about it a little more than this other physics stuff, because it can get a little... And if all you do is just listen to me in class, you might not be as prepared as you want to be. So, I'll hope you guys have a great weekend.